Hey there, and welcome. So today, we're going to look at two ways that things can grow. But you know what? Let's just forget about the formulas for a minute. This whole thing is really about spotting patterns. And trust me, once you see the pattern, you'll be able to tell these two types of growth apart like instantly. Ready? Let's jump in.
So, let me ask you something. Which grows faster? A viral video or, say, a plant on your windowsill? Just think about it for a second. I mean, they're both growing, right? But the way they grow, it's completely different. Your plant, it's going to grow a little bit each day, nice and steady, super predictable. But a viral video? Phew, that thing can literally explode overnight. And that's really the core idea we're going to dig into. Not all growth is created equal.
Okay, so let's get down to it. We're going to look at the two fundamental ways things can change over time. Think of it like this. One is kind of slow and steady, and the other one, well, it starts out slow, but then it just takes off like a rocket.
All right, first up, let's talk about the star of our show, the exponential function. Now, what makes it exponential? The secret is all in how it's built. Take a look at the formula. See that little x, the variable? It's up there in the exponent. And that one tiny detail, that's what gives this function all its crazy power.
And that really gets to the heart of it, right? When you see that variable hanging out up in the exponent, what does it mean? It means the function is going to increase, and I mean rapidly. The growth isn't just steady, it's actually accelerating. It just keeps building on itself again and again. So how do we spot this kind of rapid growth out in the wild and tell it apart from the other kind? Well, it actually boils down to one super simple question. It's all about the pattern. Are we adding or are we multiplying? That's it.
This slide lays it out perfectly. On one side, you've got linear functions. And the name gives it away, right? They make a straight line. They change by just adding the same amount, over and over again. We call that a constant difference. Then, on the other side, you have our exponential functions. They change by multiplying by the same amount each time. That's our constant ratio, or multiplier. So really, it's just adding versus multiplying. That's the whole game.
Okay, to really see this in action, let's have some fun with it. Let's set up a little competition, a microbe face-off. Imagine we've got two different microbes, microbe C and microbe D. We're going to put them in a race and see which one grows the fastest over 4 hours. Let's see who wins. Okay, here's the play-by-play. They both start out as just one single cell. Now microbe D, that's our linear guy. It just adds 5 new microbes every hour. You can see the pattern, right? 1 plus 5 is 6, 6 plus 5 is 11. It's that constant addition. But then, look at microbe C. That's our exponential champion. It's not adding, it's multiplying its population by 4 every hour. So it goes from 1 to 4 to 16, and then, whoa, things really take off. And this is the key point, you guys. For microbe D, the growth is steady, it's predictable. It's just adding 5 each time. But for microbe C, the amount it grows by gets bigger and bigger with every single step. I mean, look at the jump from hour 2 to 3. It's way, way bigger than the jump from hour 0 to 1. That's that accelerating power of multiplication we were talking about.
And here we have it, the final score from our microbe face-off. And wow, it is not even close. After just 4 hours, our linear microbe, microbe D, is at 21, which is, pretty good. But microbe C, a whopping 256. This is exactly why it's so important to get a handle on exponential growth. It can lead to absolutely massive changes really, really fast.
So that microbe race was a pretty awesome way to see the raw power of these two different kinds of growth. But now let's take that pattern spotting skill we just learned and use it on a more real-world kind of problem.
Okay, here's our data. It's the student enrollment from Martinez High School over a few years. Now, just looking at it, you can tell the number of students is going up. It's growing. But the real question is, how is it growing? Is this a linear pattern or an exponential one? Let's put on our detective hats and find out.
So remember our rule. The first thing we should always check for is the simpler pattern, which is addition. So let's just see how much it changed from year to year. Okay, from year 0 to year 1, looks like they added 90 students. What about from year 1 to year 2? Yep, 90 again. And from year 2 to 3, you got it, another 90 students. The difference is constant. It's the same exact number every time.
And this is where a lot of people get tripped up. It's so easy to see those numbers getting bigger and immediately think, oh, it must be exponential growth. But hold on, remember our definition? When you're adding the same amount each time, that steady, predictable growth, that is the very definition of linear. We found a constant difference here, plus 90, not a constant multiplier.
So the growth at Martinez high is definitely linear.
Okay, you've seen the ideas, you've seen an example, now it's your turn. Time to put those new pattern spotting skills to the test.
So here's the situation. A person named Stacy deposits $1,000 into a bank account, and the bank pays her 3% interest every year. So the question is this linear growth or is it exponential growth?
All right, this is where you hit pause, take a second, really think it through. Are we adding a set amount of money each year, or is something else happening? Are we multiplying? Decide on your answer and then press play when you're ready.
Okay, you're back. So if you said exponential, you nailed it. That's exactly right. But why? Well, think about it. The bank calculates that 3% interest on the new balance every single year. It's not just adding a flat $30 each time. Instead, you're taking the total amount in the account and multiplying it by 1.03. And that, right there, is a constant multiplier. That's the signature move of exponential growth.
So, if there's just one thing you remember from all of this, let it be this right here. When you're looking at some data and you need to figure out if it's linear or exponential, just for a second, forget about all the complicated formulas. Just ask yourself one simple question. What's the pattern? Am I adding the same number over and over, or am I multiplying by the same number over and over? It's that simple.
And really, that's all there is to it. You now have this awesome pattern spotting tool in your back pocket. So my last question for you is this. Where else in the world around you do you see this kind of multiplicative exponential change happening? Keep an eye out for it. Thanks for tuning in.